Hi. The previous lecture, I stated two results regarding the Poyer process in terms of that each equilibrium is equally likely and that any history of R red balls and B blue balls was equally likely. What I want to do in this lecture is show you why those two proofs are true. Now I'm hoping you prove these on your own. You don't even have to watch these lectures. You're just watching them to see if I did it the same way you did. But at least if you haven't tried them at this point, stop the video and try on your own just by doing some simple examples to see why these things are true. Okay, to get us started, I want to remind us how the Poyer process works. Remember, we start with one blue ball, one red ball. We pick a ball out, we look at its color, and then we add a ball of the same color of the ball that we selected. So suppose, for example, that I start out with one red, one blue. The odds of picking a red ball are 1/2. I pick out a red ball, so then I add another red ball. So now the odds of picking out a red ball are 2/3. And let's suppose I pick out a red ball again. Well, then the odds of getting a red ball in the next period would be 3/4. So this is how it works. It's really straightforward. What we want to do is see why these two claims are true. I'm going to do these claims in opposite order. And the reason why is I'm going to use the second claim to prove the first. So what was the second claim? The second claim was that any history of B blue balls and R red balls was equally likely. Let's see why that's true. It's actually really pretty easy. Let's take this sequence. So I've got one red followed by 3 blues versus one blue followed by 3 reds. So when I start this out, I've got one blue and one red. So the odds of getting the red ball are 1/2. Well, now, after picking the red ball, I've got one blue and 2 reds. So the odds of picking a blue ball at this point are only 1/3. But after I pick the blue ball, I've now got 2 blue and 2 red. So the odds of picking the blue ball are 2 out of 4. And then now for this last one, I've picked a third blue ball. I picked a second blue ball. And so the odds, I've got 3 blue balls and I've got 2 red balls. So the odds of picking a blue ball are 3 out of 5. So when I multiply all this together, I get 1 times 1 times 2 times 3 over 2 times 3 times 4 times 5. So it's 3 times 2 times 1 over 2 times 3 times 4 times 5. Now let's suppose I'm down here and I pick blue, 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 red. Well, I start out again with one blue, one red. So the odds of picking the blue ball are 1/2. But now what I've got is I've got 2 blue balls and only 1 red ball. So the odds of picking a blue are 2/3. I pick another blue. So I've got 3 blue balls and I've only got 1 red ball. So the odds of picking the blue are 3 out of 4. Well, I add another blue ball because I picked blue again. So I've now got 4 blue balls and only 1 red ball. And the odds of picking that red ball are just 1 out of 5. Well, if I multiply all these things together, I get 1 times 2 times 3 times 1 over 2 times 3 times 4 times 5. So 1 times 2 times 3 times 1 is the same as 1 times 1 times 2 times 3. These things are equally likely. Let's do one more, and we'll see why this is the case. Let's suppose I go red, blue, red, blue. So I start out, red. I've got one blue, one red. So the odds of picking a red are 1/2, and I get a red. So now I've got one blue and 2 red. So the odds of picking a blue ball in this case are just going to be 1 out of 3. But I do get a blue ball, so now I've got 2 blue and I've got 2 red. So the odds of picking a red ball are 2 out of 4. So I add another red ball. So I've got 2 blue and now I've got 3 reds. And so the odds of picking the blue ball are 2 out of 5. And so what I end up with is a total of 1 times 1 times 2 times 2 over 2 times 3 times 4 times 5. Well, let's go down and suppose I pick blue, blue, and then red, red. So if I start out with one blue, one red. So the odds of picking a blue ball are 1/2. I pick a blue, so now I've got 2 blue and 1 red. So the odds of picking a blue ball are 2/3. I do pick a blue, so now I've got 3 blue and 1 red. The odds of picking the red ball are 1 out of 4. But now I've got 2 reds in there. So I've got 3 blue and 2 reds. And the odds of picking a red ball here are 2 out of 5. So if I multiply all this out, I get 1 times 2 times 1 times 2 over 2 times 3 times 4 times 5. Well, if we look at these two examples, we'll see why this result is true. Let's look at what the claim is. The claim says any history of B blue balls and R red balls are equally likely. Well, what happens in the first case? Well, let's look at the denominator first. In each case, we're picking out of 2, 3, 4, and 5. So if I want to know the probability of a sequence, on the bottom I'm just going to get 2 times 3 times 4 times 5. That's true here. That's true here. It'll be true in the other two cases. So now I got to ask, what's the probability of getting 3 blue balls and 1 red ball? Well, here I picked the red ball first. There was 1 red ball in there, so I get a 1 on the top. Now I've got to pick 3 blue balls. Well, the first time I pick a blue ball, there's 1 blue ball. Second time I pick a blue ball, there's 2 blue balls. The one I picked first time plus the original ball. The third time I pick a blue ball, there's going to be 3. So the odds are going to be 3 out of whatever the bottom is. So for the 1 red ball, I'm going to get a 1. And for the 3 blue balls, I'm going to get 1, 2, and 3. Well, the same happens here. I get a 1, 2, and a 3 for the 3 blue balls. And I get a 1 for the 1 red ball. So here it's 1 times 1 times 2 times 3. Here it's 1 times 2 times 3 times 1. So if it were the case that I said blue, blue, red, blue, that would end up being 1 times 2 times 1 times 3 over 2 times 3 times 4 times 5. So what we get is the same probability. Notice here again, here the case I picked out 2 red balls and 2 blue balls, but the orders were different. So here it went red, blue, red, blue. Here it went blue, blue, red, red. Again, when I pick the first red ball, the probability there's only 1 to pick from. When I pick the second red ball, there's 2. When I pick the first blue ball, there's only 1 to pick. When I pick the second, there's 2. So I get a 1, a 1, a 2 to 2. So here, since it goes red, blue, it's 1, 1, 2, 2. Here, since it goes blue, blue, red, it's blue, first red, second red. But because 1 times 1 times 2 times 2 equals 1 times 2 times 1 times 2, it's going to be the same. So what we see is that result 2 holds because the order doesn't matter to me. It's get the same numbers, 1, 2, 1, 2, multiplied in different orders. So result 2, fairly straightforward. Let's now go to result 1. This is the harder one. Any probability of red balls is in equilibrium, and it's equally likely. Again, let's do some examples. Let's suppose I've got all 4 blue balls, and I want to know what's the probability of this happening. Well, the odds of picking 1 blue ball the first time are 1/2. Then it's 2 out of 3. Then it's 3 out of 4, and then it's 4 out of 5. Because what's happening is I start out with 1 blue ball, 1 red ball. Then I've got 2 blue balls, 1 red ball. Then I've got 3 blue balls, 1 red ball. And then I've got 4 blue balls and 1 red ball. So when I multiply all this stuff out, I just get all these things canceled and I get 1 over 5. Well, now let's suppose I go blue, 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 red. Well, again, I start out with 1 blue, 1 red. So the odds are 1/2 of getting a blue. Now I've got 2 blue and 1 red. So the odds of getting a blue are going to be 2/3. Well, now I've got 3 blue and only 1 red. So the odds of getting a blue are going to be 3/4. Now I've got 4 blue and 1 red. So the odds of getting that red ball are going to be 1/5. So these things cancel and I get 1 over 20. So the odds of getting all blues is 1 over 5. The odds of getting 3 blues and a red is 1 over 20. But notice I could have gotten blue, blue, red, blue. I could have gotten blue, red, blue, blue. Or I could have had red, blue, blue, blue. So that 1 red ball could have gone anywhere, right? It could have gone in the 4th spot, 3rd spot, 2nd spot, or 1st spot. So I've got to multiply this 1 over 20 times 4, and that means there's a 1 over 5 spot of getting exactly 1 red. So I've got a 1/5 chance of getting all blues, a 1/5 chance of getting 1 red. Now it also stands to reason, if we think about this for a second, what are the odds of getting all reds? Well, the odds of getting all reds is going to be the same as the odds of getting all blues, which is 1/5. What are the odds of getting exactly 1 blue? Well, the odds of getting 1 blue is going to be the same as getting 1 red, which is 1/5. So the only thing left is 2 reds, 2 blues, and what are the odds of that going to be? Well, they've got to be 1/5 because there's only 1/5 left over. So what we see here is that it looks like this is just sort of magically working. What we'd like a deeper understanding of what that magic is. So let's go to a much harder case. Let's suppose we've picked up 50, and I want to know what are the odds of getting, if I've got 50 periods, of getting all 50 blues. What are the odds of getting a blue in the first period? It's going to be 1/2. Second period, 2/3, because I've had another blue. Third period, 3/4. What about in the 50th period? Well, in the 50th period, I'm going to have 51 balls in the urn, so the odds are 50 over 51. And in the 49th period, I'm going to have 50 balls in the earth, so it's 49 over 50. Well, you can see if I multiply all these things through, they're all going to cancel out, and I'm going to get 1 over 51. So there's a 1 over 51 chance that I'm going to get 50 blue balls. And that also means there's probably a 1 over 51 chance that I'm going to get 50 red balls. Now you can say, what are the odds that I get 49 blue balls and 1 red ball? Well, let's first suppose that we get the red ball last. So what I'm going to get is I'm going to get 1 over 2, 2 over 3, 3 over 4, and so on to 49 over 50. So all those things are going to cancel just like before. But then in the last period, I'm only going to get 1 over 51, which is only a 1 over 51 chance that I'm going to pick out that red ball. Well, this is going to give me 1 over 50 times 51. But now let's think about, remember our previous claim. Our previous claim says that it's equally likely to get the red ball first or last or second or third or 17th. So this red ball could have occurred anywhere, and it could have occurred in any one of 50 places. It could have occurred first, second, third, fourth. So I've got to multiply the probability of getting 1 red and 49 blues. Just multiply that by 50, and I get 1 over 51. So now those are the same. So probably getting 50 blues or 50 reds is the same as getting 1 red, and we could sort of start to see the logic. Let's look at the probability of getting 3 reds. Okay, well, let's suppose again, since it doesn't matter, that the first 47 of these end up all being blue. So we get 1 over 2, 2 over 3, all the way up to 47 over 48. But now the last 3 are going to be red. So we're going to get 1 over 49 because there's only 1 red ball to pick. Now there's 2 red balls in there, so there's a 2 out of 50 chance we'll get a red ball in the 49th period. And then the 50th period, there's 3 red balls in there, so it's 3 over 51. Now again, all these numbers cancel, except for the fact that now I'm left with 1 times 2 times 3 over 48 times 49 times 50 times 51. This looks like a total mess. How is this going to work? Well, let's think about it for a second. I've got 3 red balls. Those 3 red balls could have occurred any one of a whole bunch of places. Well, how many places? Well, there's 50 places the first one could have occurred. Once I picked where the first one goes, there's 49 places the second one could have gone, and then there's 48 places the third one that could have gone. But if I pick place 17 and then 16 and then 12, that's the same as picking 12, then 16, and then 17. So I've got to subtract out or divide by the different orders. Well, for any given 3 balls, the different ways I can arrange those 3 balls are 3 times 2 times 1, right? Because I could have put them in 17, 16, 12, or it could be 16, 17, 12, or it could be 12, 17, 16. When I think of all those different orders in which I could put them in spots, 12, 17, 16, there's 3 places I could choose first, there's 2 places I could choose second, and there's 1 place I could choose third. So I've got to divide by 3 times 2 times 1. Well, watch. This 3 times 2 times 1 cancels out with the 1, 2, 3 on the top, and this 50, 49, 48 cancels out with this 48, 49, 50, and I'm left with 1 over 51. Well, just a moment's thought says that if I change this 47 and 3 around to 46 and 4, that'd have the exact same logic. And what I'm going to get is that there's a 1 over 51 chance of getting any number of red balls. So what we've then proven is we've proven claim 1. We've proven that any probabilities of red balls is equally likely. Now, it's easy to show it's an equilibrium, but we've shown then that it's equally likely, which is sort of surprising, which is why the Fourier process is so interesting, because it's highly path dependent. We also showed first result 2, which says that if I've got 5 blue balls and 7 red balls, that any order of getting those has the same probability. Okay, so that was a little fun math on the side, but it shows us how by constructing these models, this very simple model, we can then do some mathematics to gain insights that we never would have expected. So I might have started with a model that says, well, suppose the proportion of the probability somebody buys something is proportional to the number of previous people that have bought it, like the blue and red shirts. Okay, so that's a very simple idea. By writing down a formal model, we get 2 really interesting results. One is that any equilibrium is equally likely, and second, we get that any history with the same number of blue shirt purchases and red shirt purchases is also equally likely. Neither of those we would have anticipated, and neither of those could be figured out unless we use the model to work through the logic, which is one reason why we write down these models. Okay, thank you.